Welcome to today's Military and Aerospace Electronics webinar, Sosa System Management and Advanced Vita 46.11 Functionality, sponsored by Elma Electronic Incorporated in Fremont, California. I'm John Keller, Chief Editor of Military and Aerospace Electronics. Monitoring the health, power, and cooling of boards used in military systems is just as important as the performance of the end system. System management directly benefits the warfighter by providing reconfigurability for faster redeployment and health monitoring in the event that elements of the chassis start to fail. The 1.1 System Manager module is a key component to the Sensors Open Systems Architecture, or SOSA, technical standard. The SOSA standard describes the System Manager module as providing systems management functionality to and for managed SOSA modules, PICs, and other hardware such as power supplies and the network switches. Functionality is provided by a set of system management services. The ability to manage and interact with these system management services is enabled through well-defined sets of APIs and sensor component messages. The System Manager module relies heavily on the ANSI Vita 46.11 2022 standard system management on VPX, which provides the key components for monitoring the health, power, and cooling of SOSA plug-in cards and chassis infrastructure, and offers the means not only to find and correct faults quickly and accurately, but also to provide valuable data for predicting future faults. As a result, the System Manager module is an important element of the overall SOSA architecture. This webinar will examine what the 1.1 System Manager module is, how ANSI Vita 46.11 fits into it, and what features SOSA requires of SOSA-aligned hardware elements, including chassis management modules and individual plug-in cards and power supply units' intelligent platform management controller processors. Our speaker today is Mark Littlefield, Director of Systems Products at Elma Electronic. He's a contributor to several Vita and SOSA technical working groups, including the SOSA Small Form Factor Subcommittee, and was co-chair of the Vita 65 Open VPX Working Group, and he has more than 25 years of experience in the embedded computing industry. If you have any technical difficulties during today's session, simply type your issue into the Ask a Question box and a member of our team will assist you. You also can click on the question mark Help button in the upper right-hand corner of the screen. Additionally, we welcome your questions during today's events. We will answer as many questions as possible during the Q&A session that will follow the main presentation. But please feel free to send in your questions at any time. To do so, simply type your questions into the Ask a Question box and click on the Send button. Also, please be aware that today's session is being recorded and will be available on the Military and Aerospace Electronics website within the next week. You'll be notified by email when the archive is available. So, let's get started with Mark Littlefield, Director of Systems Products at Elma Electronic. Mark?
Thank you, and thank you everyone for attending our webcast today. Today I'm going to be talking about SOSA system management, and specifically the advanced Vita 46.11 functionality that's defined within the SOSA technical standard. So I'm going to start with a brief introduction of SOSA. I think most everyone here probably has at least heard about SOSA, if not being involved in it. But I just want to make sure that everyone's on the same level and that we all know what's being talked about here. SOSA technical standard is an open standard that defines reference or objective architecture with software, hardware, electromechanical aspects that support real-time sensing solutions. It's aligned with Vita's OpenVPX standard, as well as other standards, and the objective is governed by directives like CMOS, HOST, MORE, and others. But specifically, Sosa is designed to address a certain key domains, specifically EOIR, EW, radar, SIGINT, and communications. It's designed to provide a common architecture for all of those. It's sponsored by all the branches of government, and the Defense Department, I should say, including other government entities such as NASA and the intelligence communities. And it's very tightly linked with other standards activities within Vita, IEEE, ANSI, IPMI, and so on. So the goals of Sosa, and this will be my last slide on Sosa background, is to provide something that's open, as vendor agnostic, platform agnostic, and aligned with kind of the modular open system architecture principles. It's standardized, both software, hardware, mechanical. It's harmonized with those other standards, so we're not competing with those other standards. We're actually very well integrated with them. It's aligned with service objectives. It's cost effective in that it makes it much more affordable to be integrating these systems, much easier to integrate these systems. But also related to that is that it allows systems leveraging SOSA to be able to deploy to the warfighter faster. And that's really probably the most important thing about this. And then lastly is adaptable. And with regards to adaptability, not only dealing with changing requirements, but also technology insertions, which has been a real problem in the community for the last number of years. So let's talk a little bit about what chassis management actually is. Chassis management is defined within the SOSA context is a largely out-of-band monitoring and control mechanism. That is, it's outside the normal communications backplanes channels like Ethernet and PCI Express. Those are more reserved for the operations of the system, and the chassis management is out of that communications channel, so it's not being interfered. It's not interfering with anything operationally, and it's also not affected by any problems with the operations of the system. There's really two components to chassis management. The first one is the chassis manager module, or CMM. And sometimes people call that a shelf manager. Some people mistakenly call that a CHMC, but CHMC is actually the software that's running on the CMM, and we'll be talking about more about that later. And then the second component is the board management controller, called the IPMC, or Intelligent Platform Management Controller. The IPMC actually lives on every plug-in card, including power supplies. And there's actually can be other devices that have IPMCs as well. But then these two components, the chassis manager and the IPMC, are connected over something called the IPMB, or the Intelligent Platform Management Bus. We're going to go into more details about that in the upcoming slides. The system manager, in this diagram as you see it, is really an external actor. It's either a user, an actual person, or some application that's running somewhere that communicates with the CMM, typically over Ethernet, but there are other communication channels that it could communicate with. All of this is defined by two standards: the base IPMI standard, and then the later Vita 46.11 standard that refines and adds on to IPMI. And SOSA itself, those standards. So what does Vita 46.11 do? And that's really the kind of the governing standard, because it's a superset of IPMI. 46.11 defines a set of interfaces, data structures, message structures, and functions for autonomously monitoring a system and recovery management of system. Originally, it was targeting VPX, but VNX Plus, Vita 90 recently adopted this as well, so it'll cover VNX Plus in addition to VPX. Some of those functions, and this is not an exhaustive list, but some of those functions include the monitoring and control of chassis fans and other chassis elements, things like temperature sensors, LEDs, character displays, and so on. There's chassis sensor, IPMC, and FRU discovery, FRU being field replaceable unit discovery, and FRU inventory. It's really important for understanding what the chassis is loaded on. It's important also for understanding if anything's been replaced or changed in a chassis from, say, the last time that it was started, or perhaps even a canonical manifest of what the chassis is supposed to consist of. That could be important for security reasons. There's actual FRU control, things like powering FRUs and activating them. State management of the FRUs, sensor monitoring where if the FRUs have sensors, monitoring those sensors, and then diagnostics, self-diagnostics of those FRUs, whether those FRUs are plug-in cards or other things that can be added or removed to the system. There's the management and control of critical signals, things like sys reset and NVMRO. There's monitoring and control of the payload mode. That's a new function in 46.11 recently added that actually gives some measure of control and monitoring and configuration of the actual payload, the software that's running, or the firmware that's running on a plug-in card. There's the monitor and control of power supplies, which is somewhat different than plug-in cards, but important nonetheless. And then lastly, maintenance and system event logs. And like I said, this is not an exhaustive set, but it kind of gives you a sense of the space, if you will, of the problems and the things that 46.11 defines. So let's look at kind of how all of these pieces fit together. And this is sort of a cartoon drawing, but it kind of shows all of the pieces. We'll start with the payloads themselves and switches. This is processor cards and switch cards in the system. They're typically connected over this control plane, this in-band management, or this in-band system for communicating board to board within a VPX or a VNX Plus system. We also then have power supplies. Like I said, they can be intelligent and can be talked to, usually not over control plane, although some power supplies have that capability, but they're items that need to be controlled within the system and monitored. Then you have the actual chassis manager modules themselves. Typically, most systems only have one, but certainly there's provisions for having redundant chassis managers for reliability purposes, what have you. They, and then in turn, not only talk to the plug-in cards and power supplies, but they can talk to external sensors and other FRU information about the chassis. The chassis managers talk to the individual plug-in cards and power supplies over this IPMB. Notice there's two of them. Sosa specifically calls out the requirement for dual IPMBs. That's for redundancy, and say if one card starts acting up and jams the IPMB, that the likelihood that both would be jammed is less, and it gives a certain measure of backup control over the system. Then the last item is the system manager, and that's drawn kind of as a cloud because that's more of a logical entity. That might be software running on one of the payload cards here in the system. It might be software running in some other computer outside of the chassis, or like I said, it might be an actual human that's monitoring and giving controls to the chassis manager. But most likely it's software running somewhere. So if we switch gears and take a look at the Sosa architecture, if you will, and this is more of the logical architecture of Sosa. You see a lot of different modules here, and you know, any Sosa system is going to be made up of some combination of these modules. The one we're interested in mostly is 1.1 up here at the top. That's the system manager. And it's kind of unique in that it's one of the few that talks to everything within the Sosa sensor system. If we look at it kind of schematically, the system manager talks to other Sosa modules within the chassis. It might talk to sensor heads, that is the transmission or receiver modules that might not be in the chassis. They might be kind of on that sensor head, whether it's an EOIR sensor or a radio or something like that. But it would be outside of the chassis itself, but still part of the Sosa architecture. It could be the plug-in cards, which we've talked about. And it could be the infrastructure of the chassis as a whole. Now, what we're going to be interested in is this section here. So we're going to dive down into that section. If we look at it more carefully, you've got plug-in cards, and then you've got the infrastructure of which the chassis manager is a part of that infrastructure. The system manager talks to all of this over the in-band path, that is that control plane path. And there is protocols and messaging that makes up that. That's all defined within the Sosa technical standard. We'll be talking more about that. But so both the plug-in cards and that infrastructure, specifically the chassis manager, talks over that in-band to the system manager module over that in-band path. But the chassis manager and the plug-in cards have their own path. That's that IPMB that I mentioned earlier. So again, we're going to continue focusing on this portion here. So looking at those two components, a plug-in card payload, if you will, and then the chassis manager, these kind of, again, a schematic, a cartoon, if you will, of how these pieces fit together. They both have those Ethernet links to talk to the control plane. That's for the in-band communication portion. And then they both have that IPMB so that they can talk to each other out of band. And notice that this redundant, this dual IPMBs. Before I leave this slide, though, I do want to mention, I don't highlight it here in the slides, on the payload, there's a link from the IPMC to the application processor, whether it's a CPU, whether it's an FPGA, whatever that processor function that happens there. There is a link there that's handled through the sensor functions defined in 46.11. And I'll be mentioning that again later. So Sosa and 46.11, how does all of this fit together? So the best way to think about it is in those two domains that I mentioned. The first one is that in-band domain, which is a set of messages and interactions between that module 1.1, the system manager, and the PICs and the chassis manager module itself. And that, again, is defined by those functions and interactions that's captured within the Sosa technical standard. Then there's the out-of-band system management. Sosa defines what functions that are captured within 46.11 that form a minimum set of those functions and capabilities, and all of that happens over the IPMB. So the Sosa defined out-of-band functionality. Let's dive into that a little bit. So this is that out-of-band, that communication between the chassis manager and the plug-in cards. Again, Sosa defines what those capabilities, what the minimum set of those capabilities are. Specifically includes things like the hardware element sensor management, that is monitoring and controlling things like temperature, voltage, current, vibration and intrusion. Those are sensors that provide information to the chassis manager about the state of the system physically. There is the hardware chassis and element inventory. That is vendor identification, model numbers, serial numbers, revision ID, software and firmware load revision information, and things like that. There are hardware and chassis element configuration, actually setting parameters for the hardware, policy settings, and things like that. And those things can be changed on the fly. So the chassis manager might decide, oh, things are not going well, I'm going to change things up so that the system can continue operating and maybe isolate the bad actors and things like that. There's through recovery. Say a board is starting to act up. The chassis manager may decide to reset that particular element. It might decide actually to power cycle that particular element. And then there's diagnostics. So it might on the fly or during kind of a, hey, things are going really bad, I'm going to initiate a diagnostics, or perhaps it's commanded from some outside actor to initiate a diagnostic. It can control all of that and then collect the results. Another important thing is it can actually do firmware updates through this path. So Sosa, as I mentioned, just defines the particular set of capabilities. I'm not going to go through the whole rule set, but there are certain key rules that define the majority of what Sosa expects a Sosa-aligned chassis manager and in fact, IPMC to implement. The first rule is that it needs to implement IPMC Tier 2. Now, I should say that Vita 46.11 has a huge set of functionality and interactions, and most of those functions are defined by tiers. There's Tier 1, Tier 2, and Tier 3. There's a few that fall outside of that tier structure, but most fall into Tier 1, Tier 2, and Tier 3. And then within that, there's mandatory and optional. So what Sosa defines is that everything that's defined within Tier 2 is mandatory for Sosa. That is the required Tier 2 functions. Next, it defines that the functions that are captured within host, there's a separate document from the Navy called host that calls out specific functions that are optional in Tier 2, but that our host says are required. Those are all required within Sosa. And then lastly, there's the required functions within Tier 3. All of those are required within Sosa as well. Then lastly, probably the most important of the optional functions is the firmware firewall commands. That's relatively new in IPMI and certainly newly implemented. I think it was captured last year in 46.11. Those functions are required from Sosa. And there's a handful of other ones that I'm not going to go into, but those are the big ones that Sosa requires. You can read more about this in the 1.0 version of the technical standard, or if you want to be adventurous, there's a snapshot 1 of 2.0, and before too long, a snapshot 2 will be released. So switching gears to that in-band space, the SOSA in-band functionality is defined within the technical standards, related again to that communication from the 1.1 module to the chassis manager and the PICs. Some of those things include providing sensor component health information and health parameter settings, actually setting those ones that can be set by the system manager. The sensor manager, I should say. The generation of component health alerts. You can set alert levels and say, generate an alert if you exceed these limits. The providing of bit results. You can, the collection of that bit results so that decisions can be made based on that. Providing a sensor component states and values. So that's getting kind of down into the application space, so that you can set certain parameters at that application level. You can initiate sensor component shutdowns or restarts. That is not necessarily shutting down or restarting a board, but actually the application running on the board. But that also may include actually the hardware components reset or shutdown. That's kind of a superset of the space that those commands control. The setting or providing a sensor component modes, providing sensor component security information, initiating sensor security functions, those particular functions defined within the security domain, the security module of SOSA. The collection of sensor component or FRU inventory information. Again, that goes back to what the chassis manager can do with regards to the collection and maintenance of that FRU information and inventory information. It can initiate sensor component firmware updates, and then the overall sensor component configuration data can be updated. All of this is defined within the Sosa technical standard, but more importantly, these interactions are all defined by a set of JSON files that specifically define those interactions. All of that information is available on the Sosa website, and it's really downloadable and open to the public. So I've talked about a lot of different stuff. What's the value of all this? So the overall reason why this is so integrated within the Sosa technical standard is that these systems are complex. They're composed of multiple heterogeneous components of beyond like the backplane and the actual chassis and the chassis infrastructure, things like fans and temperature sensors and IOs and things like that. You actually have the plug-in cards that go in there. You've got processors, possibly from different vendors. You've got things like receivers and radios and other IO. You've got FPGA cards and GPUs for acceleration, accelerated processing. You've got switches for data plane and control plane. You've got the power supplies. All of these things make these systems quite complex. And so to really be able to rely on these systems and make sure that you're getting good operation from these systems, you need a mechanism for monitoring and control. That, and a lot of these systems go into kind of harsh environments, and you want to be able to kind of keep tabs on it and make sure that the system's healthy and providing good data to the operator. So specifically, the things that are central to this are correct operation of the system, secure operation of the system, detection of faults, and potentially even on-the-fly correction, and ensuring that all the hardware elements meet a specified minimum set of functionality, and that you're not inadvertently getting bad operation from the system, or from components within the system, I should say. So one example I like to point out to folks that is maybe not so critical to the operation of a system, but actually can be quite valuable, is that when a system first starts up, if you've got multiple boards in the system, any particular piece of electronics, when it first starts, there's going to be a peak of power consumption. It's called in-rush current. That's where everything is being energized, and it starts its process of starting itself. And invariably, you've got a rush of current that it draws right at the beginning for, sometimes it's only milliseconds, sometimes it could even be seconds, but that rush is excessive. And if you've got multiple boards in the system and you're not controlling them in some way, that rush is additive. So that what that results in, and this is what happened in early systems, was that you had to over-provision your power supply to deal with that huge inrush of current. And for the rest of the time that the system's operating, you have a power supply that's much bigger than what you need. If you can manage those boards and say, stagger their starting a little bit, you can manage that inrush, and you don't have to over-provision your power supplies by so much. So that's just one example of how having system management has a real benefit to the system and to the cost of the system. And then the last thing, and this is really, really starting to become important and growing. There's some people that have been doing this for a number of years, but this is really growing in popularity, is the use of prognostics. Being able to monitor the system and have the system go, hey, I'm starting to see some abnormal temperatures, or I'm starting to see some abnormal behaviors, or greater errors in these components, and so that decisions can be made with regards to scheduled maintenance, so you can actually prevent failures before they happen. So that's another really important part of the value of this. But I think you can imagine the overall value to these complex systems of having this level of visibility to what's going on to the system as a whole, and be able to manage that. So Elma has a product line based around this, and we just recently introduced a whole new upgrade to this product line that's aligned to version 1.0 of the technical standard. We have pre-programmed IPMC microcontrollers that can be used in your own plug-in card designs that give you that version 1.0 IPMC capability in your custom cards. If that fixed component doesn't meet your needs, say you have some additional functionality that you want to be able to add some of your own special sauce, if you will, to the IPMC, we license the source code for that so that you can add that special sauce and then burn it into your own microcontrollers, IPMC microcontrollers. And then on the chassis manager side, we offer this source code so you could build your own chassis managers with your own chassis manager modules, I should say, with your own enhancements, if you will. Again, your own special sauce that you might want to bring to your system design. From a hardware standpoint, we actually have chassis manager modules that we sell off the shelf. We have 3U air-cooled version, 3U VPX air-cooled version, 3U conduction-cooled versions, 6U conduction-cooled version, and then a standalone version. Now, standalone version tends to be our most popular because it doesn't actually burn a slot to use it, and it gives you a little bit more control and capability in I/O for being able to talk to elements within the chassis. And all of these offer the same Sosa-aligned, both out-of-band and in-band interfaces. And then the last thing we have is kind of a useful tool is an IPMC test card. And that's mainly for folks that are doing their own chassis managers and they want a known sort of golden, if you will, IPMC target to be able to test their software from. And so that's pretty handy for that. I'm going to dive in just into a little bit more detail, and then we're going to wrap up. The key things here, key takeaways are that our chassis manager products are all aligned to Sosa 1.0. Means that all of those commands that are called out in Sosa 1.0 are supported, as well as including those new firewall functions. That's a really important feature, and they'll support the dual IPMBs, but they also provide a full set of sensors for talking to the elements in your chassis: I2C, thermistors, analog and digital inputs, fan control. I forgot to list that there, but fan control and monitoring is all in there. Power monitoring. And LED outputs. And then from the IPMC side, again, fully aligned with Sosa 1.0, similar sets of sensors for looking at sensors within the board itself. Again, I2C and thermistors might be there, and even LED control is possible through that. So with that, I thank you all for the time and for listening. And we're going to switch over to questions at this point. So thank you.
Okay. Well, thank you, Mark. We already have some questions from our online audience. And for those who would like to participate, all you need to do to ask a question is type the question into the Ask a Question box and hit the Send button. Also, please take a moment to complete the feedback form that will appear on your screen at the end of the webinar. For our Q&A session, Gary Hansen, who is the Senior Systems Engineer at Elma Electronic, will be here to answer your questions. And Gary, right off the bat, I had a quick question, and that is, will it be at all difficult or time-consuming to update the tools that Mark mentioned once Sosa 2.0 is in place?
No. Just a second. So it should not take long for us to update the tools for our current chassis manager or IPMC. We are staying on top of the changes that are going into 2.0. I would not expect it to take more than 2 to 3 weeks to be able to update for any changes for the 2.0.
Okay. A question from the audience is the in-band system management functionality defined by Sosa for Chassis Manager or a PIC outside the scope of this discussion?
Well, so the system manager functionality, Sosa defines the interfaces to it, but Sosa does not actually define that system manager itself. As Mark had mentioned, that could come down to actually being just a person, which is not typical. Normally, it's some kind of a computer system that is configured normally to link to multiple systems, not just a single chassis or one set of chassis. It normally would be like a larger system that connects to multiple chassis and manages multiple systems together. That's not really Elma's forte. We don't get into that level of software. So it is kind of outside the scope, but it's not not unreasonable.
Okay. Where is the best place to go for tutorials or users guides to get started with Elma IPMC products such as the pre-programmed IPMC microcontroller?
Any of our sales team could provide that information to anyone in the audience. There should also be tutorials or at least user guides on our website. I have not gone onto our website to look at them recently, but there should be a getting started guide and a standard user guide for the IPMCs. And if they are interested in the IPMCs, we also offer a reference schematic that they could use for implementing our pre-programmed IPMC onto their board. But we would request reviewing that portion of the schematic prior to them actually building the board, just so we can try and make sure that we maintain, we keep everything in, within realm of what we expect.
Okay. Does a system manager compliance test suite exist, or would you expect that later if the answer is no?
I don't know of a compliance test suite. I know that Sosa has different companies that are working on, becoming compliance sort of vendors where they would run the compliance test. For Sosa, everything that's done under compliance is done through a third party. But I don't believe that there's a system manager compliance test suite currently out there.
Would you expect that at a later time?
I would expect that a third-party vendor would have a test suite. It wouldn't be a test suite that necessarily you can just pick up and use yourself, but they would have a test suite to be able to test that system management interface.
Okay. Could you please explain how the chassis manager enables users to communicate with the various modules, and what software interfaces are you seeing being used in industry by our customers?
So the chassis manager communicates to the different PICs or the different boards over IPMI or over the IPMB, which is an I2C bus. There are a set of predefined communication between the chassis manager and the IPMCs. Everything is defined through the IPMI specification, and then Vita 46.11 camps on top of that and states which actual commands are required for both the PIC to support and for the chassis manager to support. There are several optional commands versus the mandatory commands. Several of the optional commands are required in Sosa, and yeah, as long as all of the boards are meeting the IPMI specification and the Sosa required commands, then everything should communicate fine.
Okay. Do payload cards need to support the in-band chassis management function? And does ELMA have any source code to support this?
Payload boards do need to support the in-band. We do not, ELMA does not have any support package for the in-band. We only support the out-of-band.
Okay. Here's a question here. I don't quite understand it, but maybe you will. And that is TSN at 10 gigabits per second. Does ELMA have DDS running over TSN? Does that make sense to you?
TSN, I'm not sure. I am not.
All right, that's okay. We can move on.
Okay.
All right. When considering analog fan or LED control in a 3U VPX system, would there typically be NRE in order to adapt to a CMM to a system? Is there a Vita or Sosa profile to guide the location of these systems in backplane design?
So, okay, so that's kind of like a two-part question. But as far as analog signals, fan, LED control, or our standard fixed-mounted or, fixed-mounted chassis manager, there are connectors that you can use to connect up for, for monitoring your analog signals, your voltages, your fans, driving LEDs. It also would support PWM outputs to adjust your fan speed. You could connect the thermal sensors, and that there would be no NREs on that for a standard plug-in chassis or fixed-mounted chassis manager. For a plug-in chassis manager, that would be a little bit different. You would need to have a separate IPMC controller that could connect up for your fans and LEDs and for driving PWM. We have a couple small IPMC boards that could be used for that with no NREs. If they need customization, we could well do that by creating a custom IPMC for the customer.
Okay. What is the nature of the physical interface for the out-of-band management interface? Is it Ethernet or is it something else?
For the physical interface for the out-of-band management is, between the chassis manager and the PICs is I2C. External to that, or how you communicate to the chassis manager, could be done either through Ethernet or through serial port.
Okay. What is the latest revision of the chassis manager software?
It depends on which chassis manager. I'd have to look it up, but each one so the plug-in chassis managers have a different firmware than what our fixed-mounted chassis manager is. I could look up the latest revision of those. Let's see, just 1 second. So the latest version is for the fixed-mounted version is revision 3.10, build 216, and for the plug-in version is 2.0, build 46.
All right. Is the IPMC field programmable via IPMI if a new version of firmware is needed?
You can field program the IPMCs using the HPMI specification of Vita. But it can be programmed over the I2C bus. Yes.
Okay. Is there an API published by ELMA for their chassis manager, or is there a Sosa standard API that an integrator can use remotely to monitor and control VPX and VNX platforms?
ELMA does not have an API. I do not know of a standard API for remote monitoring of, and control for VPX or VNX. You could use IPMI tool. You could use SNMP. Both of those are available, and our chassis manager supports it. Our MCP could also be used, but otherwise, anything else would need to be done custom.
Okay. Do you see any pressure for the standard to move towards requiring support of version 2 of IPMI?
And a lot of the newer commands are out of the V2 IPMI requirement. So I don't see pressure to completely move to V2, but our chassis manager does support V2.
Okay. Is there a set timeline in place for the next release of Sosa, to your knowledge?
There is, but I don't know what it is. I don't know if they'll be on time, but I would assume that they want to release it. I think somewhere around the September timeframe was last I heard.
Okay. All right. Payloads need to support in-band communication, and I thought only CMM, CHMC needed in-band, like Ethernet communications. What do you see as the case?
Well, no. So the CMM, CHMC communicates out of band to all the different boards, but Sosa also requires an in-band connection to each PIC as well as to the CMM. And they do have a interface protocol that they require for that, in-band communication. So payloads need to support both in-band and out-of-band communication.
Okay. Is there a protocol defined for the chassis manager to talk to the system manager?
I don't know of a actual protocol that's defined other than that it needs to be an Ethernet link to the control plane. Protocol may be defined in the version 2 release of Sosa. I have not seen that protocol defined yet.
Okay. Would you expect that perhaps in the future?
It could well be and come out in the version 2. I just have not seen it yet on the snapshots.
Okay. Is there a way to get IPMC information from a payload card without a CMM?
You should be able to. You could always go across the IPMV using IPMI tool to get the information. The payload board itself should also be able to collect that information. But that would depend on how the payload board was designed and linked But I would think most payload boards would be able to provide that info themselves.
Okay. Just as a reminder to our audience, if you would like to participate by asking a question, all you need to do is type your question into the Ask a Question box and hit the Send button. So if you'd like to ask your questions, we still have time, perhaps for a few, so don't be shy. Where can I get the in-band JSON file that you mentioned?
Okay, that would be on, so from the technical standard, so opengroup.org, you would need to register and log in, but once you're in, then you go to the standards library, and through a pull-down menu, you can get the official release for that JSON file.
Okay. You said that the payload mode commands are a way for the chassis manager to communicate with the payload running on a board. How does that work, and does it pose a security risk?
Okay, well, first of all, there are actually 3 payload modes. So the through payload controller will set the commands and interactions dealing with the payload power, the reset, graceful reboot, or initiating diagnostics. The second is the payload interface, which is a way for the payload to access its own IPMC resources, like the sensors, without having to go through the chassis manager. And then the third would be a new set of commands, payload mode, which will indicate, what state the IPMC is in, as far as is it transitioning from a non-communication state into a communication state, or, there are, you could have a lost communication. You could have, the board is coming up, the board is up and running normally, or the board is going down. So there are different, payload modes that the board may be in, and you can, using payload mode, you can see what that state is, and then for each of these cases, the information can pass between the IPMC and payload is limited, so you can't get it out, you can't move it outside of that out of band. So there should be no security risk possible, because the in-band is where the security risk would arise.
Okay. I have a question, and that is, it wasn't that long ago that we remember when Sosa essentially was an abstraction that was designed to promote interoperability, quick systems upgrades, affordable design, those types of things. And we've gone into a tremendous amount of detail now. What would you say, how does this bode for the maturity of Sosa, having Sosa catch on in a big way, really to be, a force multiplier in embedded computing design? What is it, what does it say about where we are now in the process?
Well, I think, the movement in Sosa is opening up the doorway for a lot of multiple different contractors that before never had much of a chance with a lot of the military equipment. The big contractors all did very custom interfaces, custom software. By what Sosa's done is they've opened up the door so that everything is interoperable. You can plug multiple vendors' boards into the same system, and you can get the communication, and you can get everybody talking together. It's got faster getting equipment out to the military. It's much more interoperable, much more interchangeable. I think I think in a lot of ways it's a win-win all the way across.
Okay. I had another question come in, and that is, can IPMC do slot power cycling in the future?
That is the plan. Individual board power cycling, it's not going to be necessarily slot power cycling, but the boards should have the ability to be rebooted or power cycled themselves. You're not going to see where a backplane has the ability to shut the power down to one slot and bring the power back. But at the board level, that is the goal, that we can do a power cycle for an individual board by sending a command to that board to recycle.
Okay. Well, believe it or not, I see that we have answered the final question in our queue. So, on behalf of Military and Aerospace Electronics and Endeavor Business Media, I would like to thank today's presenter, Mark Littlefield, Director of Systems Products at Elma Electronic, and our expert commentary from Gary Hansen, Senior Systems Engineer at Elma Electronic. For those whose questions we didn't have time to answer, and I think we actually did, but we'll be getting back to you via email. This online presentation will be available on demand from the Military and Aerospace Electronics website at www.militaryaerospace.com. The link to the archived webinar will be sent to you via email within the next 24 hours. So thanks for coming. I'm John Keller, Chief Editor of Military and Aerospace Electronics.